Carol, and this video is about NP-Completeness. If you've been following the series that I've been creating here, then everything before now has been on the order of big O n to the k for any constant k. So we say these algorithms, the ones we've talked about before, are tractable or practical. Yes, even if it's big O of n to the 999th. And NP-Completeness is a class of problems with an unknown status. No polynomial time algorithm has been discovered for an NP-complete problem. So what are these classes, P and NP? So the class P are problems that are solvable in polynomial time, what we call tractable or practical problems. The class of problems NP means they're verifiable in polynomial time. So by verifiable, we mean that we can verify the answer, we can check the answer. NP itself stands for non-deterministic polynomial time. Non-deterministic is another way of saying guessing the answer. NP problems are ones that, given a solution, can we check it in polynomial time? This doesn't deal with how we got the solution. NP not equaling P is the largest outstanding question in theoretical computer science. It was first posed in 1971. So what we do know though is all problems in P are in NP. So P is a subset or equal to NP. Because we can more than check an answer, we can solve it in polynomial time. The open question though is P a proper subset of NP? There's another class of problems, and that is NP-complete. And these are known to be as hard as any other problem in NP, and we'll come back to that. I thought this would be helpful to see it graphically. And so here we have an illustration, but notice we have to cover two cases, if NP doesn't equal P or if P equals NP. And so we have the class of problems P here, which is a subset of the ones in NP, and NP-complete, some of them could be in NP, and then we have NP hard ones which are not in NP. If P equals NP though, then we say that P equals NP complete, and then we have our NP hard ones that encompass more challenging situations. Most people believe that P does not equal NP. If you could solve this and answer this question, let me know. I'll help you publish it. So there's some interesting things that happen with these different classes. So, and sometimes just slightly restating a problem makes a big difference. So take, for example, simple paths are acyclic, okay? And so is determining a path, if a path is simple, is that in P or is it in NP? So to be formal about this, we would say, given a graph G and vertices U and V and a number K, is there a simple path between these two vertices with at most K edges? And we could look at that. And so then the answer is, well, yes, there is. In fact, we can do it in linear time. So given a solution, can we determine if it's acyclical and has at most k polynomial times? So in linear time, we can do that. So we know the problem is in NP. But is it in P? So meaning, can we develop an algorithm that runs in polynomial time? Well, it turns out that this problem is in NP-complete, so no such algorithm probably exists. Some other thoughts along this line is, like, if you have an Euler tour, a cycle that traverses every edge exactly once, well, that's on the order big O of E. But a Hamiltonian cycle, which is a cycle that traverses every vertex exactly once, whereas Euler was every edge every once, is NP-complete and has a big O of n squared times 2 to the n. Very different. Very different. Additionally, like 2 conjunctive normal form, or CNF, meaning can 2 Boolean variables be combined with ands, ors, and nots to produce a true, then that's polynomial time. That's if you use 2 variables. You increase it to 3, and it's NP-complete. In fact, it's NP-hard. And that's just amazing to me. Slight changes and very different. So let's talk about linear programming, the problem. Is it in P or NP? And you can think back through previous videos of, well, how did we calculate that? What were the steps, and what are they in terms of n, and how can we come up with that? So, and we could even talk about this, is it even in NP-complete? So what we really want to do is cast the question as a yes-no question. So to determine if it's in NP, can we in polynomial time determine if a solution is correct? And that'll help us to know if it's in NP. And yeah, we can. We can have a solution, and we did that in my other video. Here's the basic solution, and we could see, yep, it still holds true, for example. And so, but to determine if it's in P, though, can we, in polynomial time, calculate a solution? And so we can. And so, yes, linear programming is in P. Interesting, though, integer linear programming, though, is NP-complete. Just saying, okay, all of the coefficients, though, have to be whole numbers. Well, that constraint actually makes it much harder. So if you're asked to implement, so how can knowing about complexity help you? Besides just it's cool and understanding different classes of algorithms and being well prepared for the test. So let's say your boss says, hey, we need you to implement this problem, and you do some research and you're like, it's NP-complete. So then don't waste your time coming up with an exact solution, but use approximations. You can look at chapter 35 of Introduction to Algorithms. You could come up with heuristics to get close. You could, and it depends on the problem, right? So don't get me in trouble with your future boss or your current boss. And so you need to pick which one. But you might just need to accept that an exponential runtime is the best you can do. Or could you solve a subset of the problem? So maybe the general case is going to be NP-complete, but for your situation, there's some additional constraints that you're always going to be trying to solve for the problems you deal with. And so maybe that subset, though, isn't necessarily NP-complete. So how do we know if a problem is NP-complete? And so, and this is a shift from what we've been doing before and what you've probably seen in other parts of algorithms class. Instead of a big O, which is, it fits in this class, what we're trying to say, instead of how easy a problem is, we're trying to say how hard the problem is. Instead of trying to prove an efficient algorithm exists, we show that it's not likely to exist. So we reframe the question when we're trying to answer, is it an P or an NP, from just an optimization problem to a decision problem. So often we have optimization problems. For each input, what's the best output is a classic optimization problem. For example, shortest path. Given a graph and weights, what's the shortest path between vertices U and V? And we can do that, for example, with Dijkstra's algorithm and others. So NP-Completeness applies, though, to decision problems, yes-no problems. So usually we can just bound an optimization problem to make it a decision problem. For example, instead of shortest paths, what about path? Namely, given a graph and weights and a threshold k, notice that addition, is there a path between two vertices that has at most k edges? Okay, so we change the optimization problem to a decision problem. Can we find a path that has at most k edges? And so then we're solving a decision problem. So this makes problems easier, or at least no harder than the optimization problem. And typically, if we can solve the optimization problem, we can solve the decision problem because it's a subset of it. So the decision problem version is easier. If we can prove that the decision problem is hard, then we can prove that the optimization problem is hard. So we'll be focusing on decision problems. Now, how do we come to classify an algorithm as NP-complete? Well, almost every NP-complete proof makes a reduction of one problem to another. If, for example, you're looking up on Wikipedia about an algorithm, you're going to say, oh, this reduces from 3SAT or some other well-known one. So let's get into that. What is that all about? First, let's make sure we have a vocab. An instance means one particular set of inputs. What we want to solve, we have a decision problem A, and let me back up. We're talking about polynomial time reductions. We'll talk about other reductions in a second. So we've established the vocab term, and so we want to solve a decision problem A, and we want to do it in polynomial time. We already have an algorithm B here, and we know that it runs in polynomial time. And so if we could just take a polynomial time mapping for any instance in A, we'll say alpha, and map that so that it could fit into B, and we'll call those inputs beta, such that if the answer to alpha is yes, it's yes only if the answer to using beta is yes. So what we've done is we've reframed the problem to be able to come up with a solution. We have some machinery that already works, this algorithm B, and it does a good job. And so we're saying, instead of rewriting everything from A from scratch, we'll just write a little wrapper for A that will map things to B. And so here's an image from Introduction to Algorithms that shows this pictorially. So you could imagine the bigger box as our big box, and so this is how we solve A. We say, okay, what's our inputs to A? Well, in polynomial time, we're going to map those to B, and then run it with B in polynomial time. And if it's yes, we're going to say yes, and if it's no, we're going to say no. And so then notice this outer box here then is a solution to A, but inside the box is B. So we do things like this in code. We'll have a little wrapper, and we'll call some other method, and whoever's calling that method doesn't really need to know and be bothered that inside it's really calling some other method. but it works. If you're like me, this maybe could make more sense if we put it into code. So here we're declaring we have a method, a function b that takes parameters beta and returns a boolean. And then we're declaring, okay, we're going to solve A, and you give it given arguments alpha, and we're going to call this method to transform args alpha so that they're ready for B here, and then whatever B returns will return. And a key point is that transform args only takes polynomial time. And if B takes polynomial time, then we're guaranteed that A takes polynomial time. So that's just saying the same thing in a different way, using pseudocode instead of graphics. So the way what we say is we reduce problem A to solving problem B. And we use the easiness of B to prove the easiness of A, because it's all based on B. So let's talk about doing this in reverse though. For NP-complete, we want to show how hard a problem is, not how easy it is. So let's assume that we have a problem A that does not have a polynomial time solution. And we'll come back to how do we get to there. But let's say we've already determined A does not have a polynomial time solution. And we can take any instance of problem B and map it to problem A. So then we can use a proof by contradiction to show that no polynomial time solution can exist for B by assuming that B has a polynomial time solution. Then we can solve all instances of A using B, using what we just talked about, the polynomial time reduction. But that's not possible because we've already said A does not have a polynomial time solution, so B cannot have a polynomial time solution. But otherwise, we could have a polynomial solution for A. So now let's apply this to NP-completeness. For NP-completeness, we're going to use polynomial time reductions in reverse to show that B is NP-complete if we have an algorithm A which is NP-complete. And so assume that we already have a problem that is NP-complete, that's a prerequisite, and that we have a polynomial time mapping to go from A to an instance of B. Then using proof by contradiction like we just talked about, we can show that B is NP-complete. Great. And the way we do that is we assume that B has a polynomial time solution, then we can solve all instances of A using B, using our polynomial time reductions, but that's not possible, so B cannot have a polynomial time solution. So here's some things to think about. There's a famous article a couple of years ago by Karp, and it's his 21 NP-complete problems. Pick one of those, describe the algorithm, and describe how we know that it's NP-complete. And then another exercise would be draw the whole hierarchy of 21 problems. Show which problem was reduced to a known NP-complete problem for each one of Karp's 21 problems. And that would be a good exercise left to the interested student. Well, thank you for watching. I hope that was helpful to understand NP-completeness, NP, P, different classes, and how do we determine that something is NP-complete. Thank you.